In this problem, we have an opportunity to see how the Poisson's ratio and a stress influence a change in diameter of an axially loaded bar. Okay, so we have a bar with an elastic modulus of 210 gigapascals, Poisson's ratio of 0.26, has a diameter of 1 centimeter, length of 11 centimeters, and there's an applied force of 1 kilonewton. The question is, what is the change in diameter? So for this example, we're going to use the methodology suggested by Crandall, Dahl, and Lardner. Namely, we're going to break our problem into aspects of equilibrium, geometric compatibility, and constitutive equations. Now, sometimes it's a little bit of a stretch in terms of, okay, which column do we place certain aspects of what we're trying to solve? And sometimes it's not the fastest way to break it down in these three categories, but we have a framework that might help us if we get stuck. So for equilibrium, let's just put out that we have an axial load on a bar, and we can even break it down into thinking that there's going to be an internal force in that bar, and that we can relate the internal force to the force, they're the same, and the cross-sectional area A to get the longitudinal stress or axial stress, sigma. For geometric compatibility, what we have is that force pulling this bar under tension, and the bar itself is going to extend, like we see here, with by some amount delta, and because we have a Poisson's ratio playing a role here, the diameter is going to shrink. So you see that this bar is going to get a little bit smaller in its diameter. Now, I took some liberties here to put this constraint on this end. Really, that means the constraint would mean that at these points the diameter is not actually changing. Okay, but I thought it was easier to see it this way in terms of the contraction and the extension by having one end fixed, at least preventing the horizontal motion. On the side, maybe it could slide inward. So the change in diameter is going to be given by how much contraction do we have, say, on the top and on the bottom, or, circumferentially, right? Or radially, sorry, not circumferentially, radially, okay? And, and we can describe that as delta D. Now, the delta D actually has a role in describing what we'll call the latitudinal um, strain. Okay, so longitudinal would be along the bar, and latitudinal is going to be orthogonal to it. Okay, so the latitudinal strain is going to be this change in the diameter over an initial diameter d. Okay, and I guess that was given as 1 centimeter in this question. Let's now come over to the constitutive equations that we're going to use. This sigma longitudinal, okay, which is the same as this sigma over here, this sigma longitudinal is equal to E epsilon longitudinal. This comes from Hooke's law. And we have a Poisson ratio that we can use to describe the relationship between the latitudinal strain and the longitudinal strain. And we kind of saw that behavior here already. But now this is in terms of strain, and it introduces the Poisson ratio, new. After we've got these sets of equations, we can go ahead and start to manipulate and combine things algebraically. So we have this longitudinal strain is equal to E times epsilon longitudinal, and we have a longitudinal strain down here, so we can rearrange things so that epsilon longitudinal is equal to negative epsilon latitudinal over nu. We see there. And we can say that this latitudinal strain is the delta d over d, so we can substitute that expression in. So we have a delta d over d, still nu is in the denominator, and we have a minus E times delta D over nu. We're interested in the delta D, so it probably makes sense to, at some point, rearrange things so we have a delta D on the left side, and that's going to be equal to the minus nu times D times sigma longitudinal all over E. Again, just manipulating this equation right here. Well, what is the sigma longitudinal? The sigma longitudinal is going to be the force divided by pi d squared over 4, or the force over area. So the 4 is like, in the denominator of a denominator, and we have, so that can come up on the numerator. So we get a minus 4 up there, times the force F, times nu d, so that's taking care of the sigma longitudinal, and in the denominator then we have the pi d squared times the E. All right, so now let's go ahead and plug in some numbers and see what we get as a result. So for that, we can start with Google. That's fine. All right, and wait, where did it go? I want to use this. Ah, there it is. Okay, that was all right. That's fine. So Google, and maybe we'll make it really small. All right, here, just so we can fit things. So we're saying that we want a minus 0.26, that's the Poisson ratio, times the diameter, so we'll just say 1 centimeter, 1.0 centimeter, times, oh, I see, I was doing this one. Okay, well, we can do the sigma long as force over pi d squared over 4, I guess. So let's do force, which is given as 1 kilonewton, so 1,000 newtons. Okay, and then we'll do the pi times, we've got diameter 1.0. Okay. So that's going to be 1.0 centimeter squared divided by 4. Okay, that works. I think that's good, times 1,000 newtons. And we need one more parenthesis to knock out that. So I think that's good. And then we just gotta divide by E. So E is, in this case, is 210 GPa. All right. Let's see if that math gives us at least something in the right units. So it's a very small amount, 158 nanometers. Okay, that's pretty small. Nanometers are 10 to the minus 9 meters. Let's see what happens when we do the calculation using Colab. All right, so here we'll go ahead and create another new thing. Nope, it's selecting something, so I'll do it here because I don't have much space. I want to see parameters. So we've got a new notebook coming up. We're going to do import numpy as np, control enter, and it already gave us code. Okay, that was nice of it. And so we have some parameters. We have a force that was given as 1,000 newtons. So I'll put that hashtag newtons. We have a nu, which is 0.26, and that's just a Poisson's ratio. So it's unitless. We have a diameter, which was given as 1 centimeter, but let's just do e to minus 2. Okay, and then that will give us units of meters. We have an elastic modulus, yes, and that was what, 210 maybe? Okay, 210 gigapascals. So we have 210 gigapascals, but that's going to be, so it's E9, and that will be pascals. All right, so then the delta D, or maybe we'll just call it delta D like this, I don't know. That looks weird too. So we'll just say delta D is equal to minus 4 times F I don't know, we can write it out, times nu times d. And I guess we could have canceled out these d's, but let's just go ahead and leave it. np.pi times d squared times e. Okay, I think that's right. And then we'll just do a print delta d is equal to, and we'll do np.round. So this is going to be delta d. Okay, now it's all the way in nanometers. Okay, so this is something, well, like if we just leave it, let's just leave it, we're probably not going to see something that's going to help us much. All right, if we just leave it in meters, uh, I'm guessing it's going to, yeah, just give us a 0 because it's such a small amount. Okay, so if I did like 10 digits, right, then like it would, okay, it's starting to get us closer to something that makes sense. Okay, and that's interesting because this number um, uh, is it's a little bit hard to understand because you're like, wait, is that a micron? Is that, what is that, nanometers? So if I want to get something in nanometers, I'm going to multiply by 1e to 9. Okay, or, and then I don't need 10 digits. I guess it's absurd. I guess I can leave it and I'll change this to nanometers. So it's probably going to be, yeah, that's a little bit absurd, but we see that we get, just like one decimal place would have been sufficient. So minus 158 nanometers. And that's what we got when we used Google. So uh, I'm glad those two things agree. Thank you very much for watching. I hope you found this example helpful.